Welcome back. This is the second to last video in lesson 2. In this video we're going to talk about vector addition and scalar multiplication in R3. Before we do so, let's go back and recall that we've just defined our first operation called the 2 norm. Which is a map between vectors in R3. It has a unary operation. It is a unary operation. It's a single input. And it gets mapped into R. The 2 norm in R3, and you have to be a little careful because we are using the exact same notation as we did for the 2 norm in R2. This maps vectors in R3 into the set of real numbers. Remember that when we talked about map notation, the semicolon represented the idea, where did you come from, where did you go, where did you come from, Cotton Eye Joe. So in this case, where did you come from, where are you coming from, is called the domain. It's the set of possible inputs. The domain of the 2 norm is R3. And then the set of possible outputs is called the codomain. And that's the thing after the arrow. So what we're saying is, the 2 norm takes in vectors in R3, a single vector in R3, and outputs scalars. We had more than this. If we had a vector in R3 given by the coordinates perhaps x1, y1, z1, and we can tell it's a vector because of the brackets, then we knew that the 2 norm of the vector x was simply the square root of the sum of the squares of the components. Sometimes it is useful to be able to look at the square of the 2 norm, which is to clear the square root. If I square both sides of this equation, I get it's the sum of the square of the components. We're going to see this form of the 2 norm again in lesson 4 when we talk about inner products. Excuse me, that's lesson 3, called the dot products. We saw an example of how to calculate these in the last video. For vector addition, we use a very similar definition as we did in R2. Vector addition is going to be a binary operation. There are going to be 2 inputs. Remember, in this notation, here, this is called vector addition. Vector addition is a map with 2 inputs. Binary operation with 2 inputs. The size of the left input is going to be a vector of size 3. The size of the right input is another vector of size 3. And then the vector add is going to output vectors of size 3. Okay. With this being said, if we let the vector x be equal to x1, y1, z1, and the vector y be equal to x2, y2, z2, we define the sum of these vectors, x plus y, using the component form that we saw previously. You can tell this is vector addition because on the left-hand side we have a vector of R3, on the right-hand side we have a vector of R3, and the vector addition proceeds by pulling the addition into the individual components, just like we did before. I want you to be very, very cognizant of the fact that these addition signs are different. This is what we call a vector addition. This is a scalar addition. So a single vector addition in R3 represents 3 individual scalar additions in R, which is quite powerful. The second operation that we're going to talk about, maybe we want to see an example before we go on. If we have 2 vectors, perhaps we're going to take the vector x is 1, 0, 1. And we'll take the vector y as -1, 1, 3. And if we want to add x and y, -1, 1, 3, we literally just add the components. 1 plus -1, 0 plus 1, 1 plus 3, and we get 0, 1, 4. Oh, that's the operation of vector addition. Scalar multiplication is a similar generalization from R2. And we'll call it scalar vector multiplication. Scalar vector multiplication is going to be represented by a dot. It is going to be a binary operation. It's going to require 2 inputs. The left input is going to be a scalar from the real numbers. The right input's going to be a vector. And when I multiply the scalar times the vector, I'm going to output another vector. So, scalar vector multiplication maps a scalar and a vector into a vector. And the vectors are both in R3. If we let C be a scalar, and we let x be a vector in R3 with x given as the 3 components x1, y1, z1, we define scalar vector multiplication c times x. You could tell this dot is a scalar vector multiplication because on the left-hand side we have a scalar, and on the right-hand side we have a vector in R3. And that's kind of an important check that you want to have. So here this would be c times x1, y1, z1. Just as we did in R2, we translate this single multiplication between a scalar and a vector into 3 scalar multiplications simply by bringing in the vector multiplication to individual scalar multiplications. Let's take a look at an example. So suppose that we have a vector, let's call this vector z, and we'll say that maybe it's like 1, -1, 3. and we'll find the scalars 0 times z, which would just be 0 times 1, negative 1, 3, which of course is just 0 times 1, 0 times negative 1, 0 times 3, which would be 0, 0, 0. Of course, zeroing out a scalar, the zero scalar produces this. And we could also find another version, which is perhaps the negative version of z. So I'm just going to multiply z by negative, which would flop the orientation. So it would be in the same direction. It would just be 180 degrees along that line. So here we would have, this is negative 1 times 1, negative 1 times negative 1, negative 1 times 3, which of course would be negative 1, positive 1, negative 3. Notice, these vectors are in the same direction. This vector can be written as a scalar multiple of this vector. Their orientations are opposite. And I think this is a very important point to make. We say two vectors in R3 are in the same direction. So perhaps you have these two vectors, x and y. These two vectors are in the same direction if and only if. So when you see IFF, this means if and only if we can write one of the vectors as a scalar multiple of the other vector for some scalar in R. And that scalar might be C can be positive, negative, or 0. So directions in R3 have to do with whether or not one vector can be written as a scalar multiple of another vector. And what I mean by this is if you have a vector x, this vector, if you look at the set of all scalar multiples, this is going to create a one-dimensional subspace of R3, which is going to be in the entire line, right? So this would be x. Here you would have 2x. Here you had negative 1 times x, negative 2 times x, and you could create this entire line. And we say two different vectors on this line are in the same direction because one of the vectors can be written as a scalar multiple of the other vectors. What I want to say is there is something called orientation. We can also speak about orientation. Orientation has to do with the sign of the scalar in this direction. So x and y have the same orientation. And direction if x equals c times y and c is a positive number. Which means if you had, let's say you had x in this direction, y in the same direction, so y is a scalar multiple times x, but not only is it a scalar multiple, it's a positive scalar multiple, so you're scaling x positively. We would say that they are oriented in the same direction. We would say that they are oppositely oriented with opposite orientation if and only if x is equal to c times y and C was negative. So think about this. You have this vector x going in this direction. You have another vector y in the same direction. It's on the same line. They're collinear. But to get from one to the other, you have to multiply the first one by a scalar, which is negative. So these are oppositely oriented. This idea is going to come back in a major way when we talk about directional derivatives and gradients. This will be later on in the course, and it is a very subtle concept. For now, I think it's important that you note this. Okay, in the last video of this section, we're going to talk about spheres and cylinders in R3. See you in the next video.